Sadly, we've come to the last kinetics video. Tissue in hand, right? Catch those big tears. This is really simple. We're just going to look at some basic methods of increasing reaction rates, things that we would actually do in the lab. Now, they mention a few. Not mentioned are also a few that we should put on paper. Easy way of increasing your reaction rate. How about increase the concentration? What if I had a solution and I increased the concentration from like 1 molar to maybe 5 molar? If I have more of the active particles, there should be more collisions, hopefully more effective collisions, which should then produce more products. So you can always try increasing the concentration. That should increase your reaction rate. Another common way of increasing your reaction rate, increase surface area. So for example, let's say I wanted to do a reaction with, I don't know, like iron. One option, in first year we actually do this reaction, it's like a single replacement where you take a solution of copper ions, like copper sulfate or something, and you put in some iron, any kind of iron, and it's a replacement, like you should get then the copper produced, and you collect the copper and dry it and all that good stuff. One method is to use an iron nail. That works. Yeah, the next day some of the iron has reacted, like if you take the mass of the iron nail, it's less. However, you do have to wait overnight. Or you could use what's called iron filings. Iron filings are basically like almost a powdered or granular form of iron. Tiny little pieces, and you can get different meshes, so they can be kind of like little chunky pieces of iron, all the way to like almost a powdered iron, which is kind of dangerous actually. It's very small particles. If you increase the surface area, there's more places for collisions to occur. And again, reactions should go faster, so you probably would have guessed these right, like on a test or a quiz. But we'll make it official, we'll put them on paper. Another one that I think you probably would have guessed, increasing the temperature, right? Because again, if we increase the temperature, the particles have more kinetic energy, they should be moving faster, more collisions, hopefully more effective collisions, which should lead us to more products formed. Now, let's look at this graph. It's called a Maxwell-Boltzmann curve. And I think we kind of mentioned this back in maybe the gas chapter, that, temperature and average kinetic energy are proportional. But if you just take a thermometer and throw it in a sample of water or whatever, you're just going to get that average temperature reading. There are always some particles with more kinetic energy and some particles with less. You don't know that by looking at your thermometer. It's only going to give you the average amount of kinetic energy, or the average temperature reading. Okay, now again, sometimes it doesn't seem like we personally need to add any activation energy. Great example is like you mix two solutions, they form a precipitate. You can do it at room temperature, boom, the precipitate forms. Now obviously if I increase the temperature, the precipitate might form faster, but it doesn't seem that you personally needed to add activation energy, because some of the particles themselves already have enough energy to start the reaction. So here, if I look at this curve, let's look at the blue curve for lower energy. Now, even though we might be at a lower temperature, there are still a small fraction of particles with enough energy to start the reaction. So if this point here is like activation energy, the minimum amount of energy required to start the reaction, there are still some particles with enough energy to start the reaction. This sample right in here, these guys can start the reaction themselves. And again, it doesn't seem like I need a spark, or I don't have to add any heat energy, because a very small sample of the particles can start the reaction themselves. They have enough energy to get it started. By increasing the temperature, you just kind of increase the fraction of particles that have activation energy. There's more particles now that have enough energy to start the reaction. Now this whole sample in here, these guys all have enough energy to start the reaction if I'm at a higher temperature. Oh, so again, it still might not seem like I need an outside source of energy because the particles themselves have enough energy to start the reaction. But again, by increasing the temperature, you've increased the fraction of particles that can start the reaction themselves. And finally, another option, which you probably would have guessed as well, a catalyst. A catalyst obviously makes a reaction go faster. I think everybody knows that, but they don't always know why. A couple options. This is always true. A catalyst lowers the amount of activation energy needed to start the reaction. This. Always true. So if we look at some of these potential energy diagrams, I might have a reaction uncatalyzed. Okay, so my reactants are at a low energy level. I need to gain all this energy, and finally I form products. This might be my activation energy. I have to add all this energy to form products. There we go. So let's mark that in. Activation energy. Uncatalyzed. That's a lot of energy. I don't know. Let's pretend it's like 100 kilojoules. I have to add 100 kilojoules of energy to get this reaction started uncatalyzed. Notice too that it's an endothermic reaction, so I usually do need quite a bit of activation energy. With a catalyst, this is just lowered. So now I might need less energy to start the reaction. Now maybe this is catalyzed. So now this is my new activation energy. So now maybe it's like, 70 kilojoules with a catalyst. So the reaction should start faster because, again, I don't need as much energy to get the reaction started. I don't need as much outside energy to start the reaction. That's the main reason why catalysts make reactions go faster. They lower activation energy. Now, here are some other things that could happen by using a catalyst. Some catalysts work by weakening the bonds of the reactants. If they start to weaken those bonds, again, I might not need as much energy to get to that activated complex, that transitional state where the reactants are starting to break bonds and get ready to form new bonds. Some catalysts provide surface area. There's something called a boiling stone. It's basically like these little limestone pieces. They look like you'd go just dig them out of your garden, these little limestone pieces. All they do is provide surface area for particles to collect and react. That's it. If these particles kind of are attracted to the catalyst, then they all join together and they can react faster because they're more likely to be close to one another. So, different catalysts will work in different ways, but they will always lower activation energy. And this is also true as well. They will never be consumed. They're not part of the balanced equation. We're going to look at this one in class. We're going to look at the decomposition of hydrogen peroxide. Hydrogen peroxide will decompose to form water and oxygen gas. And if it bothers you, we'll balance this equation. There we go. What you'll see is something like this. Ki. Hydrogen peroxide will decompose on its own. That's why often if you buy peroxide in the store, it's in a brown bottle. Because just UV light will decompose hydrogen peroxide. I guess it's not completely on its own, but just the energy from the surrounding lights, or if you had it next to a window or something like that, it'll just naturally decompose. If you put a bottle or like a cup of hydrogen peroxide next to a sunny window, it'll start to look kind of fizzy over time. Like if you leave it there for an entire day, well, that's the oxygen being released. I don't want to wait that long, so we'll use a catalyst. We'll use this potassium iodide catalyst. It is not part of the balanced equation. There is no potassium or iodine anywhere in this reaction. So often they'll write it like on top of the arrow, which shows that this hydrogen peroxide decomposes with the assistance of a potassium iodide catalyst. It will work without the catalyst. It just goes much faster with the catalyst. Now, some catalysts can actually be collected and used over and over again. Like these boiling stones, these little like limestone pieces, you just fish them out and you can use them over and over. They're just providing surface area for particles to collect and react. They're not changing in any way. With this potassium iodide one, after the reaction there will be signs of iodine present. It's not chemically changing whatsoever. It's just helping to lower the activation energy so the reaction goes faster. So the first 2 points will be true of any catalyst. Lowering activation energy, and they're not consumed whatsoever. They're not part of the balanced equation. Some special catalysts will work kind of in the middle by either weakening the bonds or by providing surface area.